Okay, we're going to begin the session on PIR. And great. And the first talk is going to be given by Alex Hoover. Take it away.
Thanks. So yeah, I'll be talking about some work I did while I was at Google, which is joint work with Sarvar, Pino, and Kevin, who are both in the audience. All right. So this is PIR 2. So I should just say that the first 3 sections are going to be relatively short. I'm really just going to be using PIR as like a motivation to build this thing called an invertible PRF, which is something we define and build in the paper. So if you kind of tune out for the first 3 sections or get lost, you can jump back in the fourth one. But I'm going to try to motivate the problem. This is PIR 2, so I assume most people know what PIR is. It's a protocol between a client and a server, where the server holds some large database of an element, and the client wants to access a specific index X. And they engage in some protocol, and ideally in a PIR, the server will learn nothing in a computational sense about the client's index X. But the client will learn the database element that they're interested in. And there's this really well-known lower bound for a single server computational PIR that the server has to read its entire database in order to process the query privately. And there are a few ways to get around this. We've seen there was a talk in an earlier section about doubly efficient PIR, but I'm going to be following Ling and be talking about PIR with client preprocessing. So here we have an expensive offline phase where we do like work that's potentially linear or even super linear in the database. And then the client will process some set of hints or some small state. And then in the online phase, they'll use these hints together with their index X to run a much faster online query. So this online query should be sublinear in the database size, ideally like square root of the database size is what kind of the state of the art is. And the specific question that we target in our work is what happens if the database changes after this offline phase. So the client's done some preprocessing on a specific database state, but if even like one element changes in this database, it's not clear whether or not the client could use the hints in an offline phase to speed up a query at all. And so our model of updates that we're going to be taking here is that every time an element changes in the database, the server will just tell the client, hey, I changed this element from this old value to this new value. And it turns out that it just so happens that all the schemes that have been proposed, as far as I know, can work in this model, where the client just manually will update their hints to be in line with the new database state, although they require this full pass that we'll dig into later. And there are alternative approaches for those of you who know like the Bentley-Sachs transform, or you could try to store operations, but I won't go into the downsides of those, but I'm happy to talk about it offline. Okay, so I'll just be talking about the prior work that we build on pretty much directly, and these are 2 PIR schemes called Piano and RMS, which is the authors of the latter paper. And I'm only going to be talking about it at a very high level, only to motivate the IPRF. So both of these schemes kind of conceptually divide the database into what I'll call blocks, each of width W. So B blocks of width W, you can think of these as square root in, or as like a matrix with rows and columns, if that's better for you. And so an index belongs to a particular block, and it'll correspond to a specific offset, so how far into the block that index is. And a set, when I say a set, it'll just mean that I'm taking one element from each of these blocks. So if I give you B offsets, that fully describes a set. And in both of these schemes, their hint structure, right, these hints that are processed in the offline phase look like this, again at a high level, where we compress a set. So we take a random set, but it's going to be pseudo-random because we compress it with a PRF key, which is used to generate offsets. I just run PRF on this key at 1, 2, all the way up to B, and I get uniformly random outputs. And so I store this key together with some what I'll call parity information, which is just the database XORed at those particular elements. Okay, so I'm using and I need lambda W of these hints because I want every single element of the database to appear in at least one of these sets. So lambda here is the security parameter, and W, remember, is like square root in. All right. And so updates in this model, or for these schemes, would look like this, where I tell you that I've updated a specific element X, and you scan through all of the hints, and you do what I'll call a membership check. All a membership check is for these schemes is just you run the PRF for the specific block to see if it matches the specific offset. This is just checking whether X is in that hints set. And then if it is, we take off the old value and we add on the new value. Right? We just update the parity information to be in line with the new database state. Very simple. But this takes a full pass over the hints, and what our goal is going to be to do is to only update the hints that have to be updated. For any particular X, There are actually very few hints that contain X, and so we only want to touch those. We want to do a much faster update. And so that's what we do in Plinko, and we combine kind of two insights. So we solve this efficient hint finding problem, as I call it. We're given an index X. We want to find all the hints that contain X. And we do it with two main things. We use this new offset generation and then this more major thing, an invertible PRF. Okay, so I'll just have one slide on modifying the offset generation. All I'm really doing here, I think of it as transposing the keys. Basically, before I had one independent key for every hint, but that, at least to me conceptually, is going to be hard to search over. So I want to use the same keys for all of the hints. So all I've done in these equations is I've swapped the J and the T. So I have one key per block now, and then the input to the PRF is the hint index. So instead of having a key per hint, I now have a key per block. And this is nice because the entire distribution of these offsets is the exact same. All of them appear uniform, or pseudo-random, uniform, and independent. And so now, and also now we're using the same keys, so we can hope to do a faster hint finding. And for faster hint finding, we're going to introduce a new tool that, as far as we know, hasn't existed in the literature, called an invertible PRF, which is just an extension of a PRF. So it's a pair of functions. The first one is just a normal PRF. It's a keyed, what we'll call the forward direction, that appears pseudo-random on different inputs. And now it has a backward function as well, where it takes the same key, but it can compute the pre-image of a particular output. So this is usually like a bad thing, right? You wouldn't want to compute the pre-image of like Shah. That's a not desirable property, but for efficiency here, we want this. And then the game looks a lot like a PRP game, for those of you who are familiar, where I'm just trying to distinguish a forward and backward oracle from the random function inverses. Okay, and I should say that we actually don't need the strong security for the PIR application, although we do achieve it in our construction. We actually only need the traditional IPRF security, because we really care about this efficient inversion for our application. And so once we have an IPRF, we're pretty much done as far as the PIR is concerned. Because now to find a hint efficiently, we just take our X, we look at the block key and the offset, and we just invert. We just run the IPRF backwards, and we get out some indices, J1 to JP, and these are exactly the hints that contain X. And I should say that with this forward and back, in the paper we discuss it more, but it's tempting to use something like a PRP for this, although you have to be, you can't use it directly, at least on top of like Piano or RMS, because it's very important that these are distributed and look independent. Happy to talk about that more offline as well. But now updates in Plinko are just a single loop, so we just run the IPRF inverse, and then we loop over those hint indices and update exactly those hint indices. And of course, each X appears in at most like log W with extremely high probability hints. And so this whole thing runs in like polylog W time with overwhelming probability. Awesome. So now, if you tuned out, you can tune back in. I'm not going to be talking about PIR anymore. I'm just going to be talking about how we build this IPRF, because I think it's conceptually very simple, and I think everyone here can understand it. Okay, so I'm going to start with just talking about what a random function looks like, and I'm going to model it as throwing in labeled balls uniformly into im bins. So in is my range, or my domain, and im is my range. And so computing the forward direction is going to amount to finding a specific bin for a labeled ball. So I ask you, which bin did ball 5 land into? And then computing the inverse is going to be enumerating all the balls that landed in that bin. Okay, so we want an efficient evaluation of both of these. And we're actually going to just start with the simpler problem of trying to do this without not worrying about the labels yet. Let's just try to get the number of balls distributed among the im bins, and also have these two forward and backward evaluations to be efficient. So this is called the multinomial distribution. If I throw in balls into im bins, it follows something called a multinomial. And I want to sample a multinomial in im so that I can have both of these evaluations be efficient. So given a ball, find which bin it's in, and given a bin, enumerate the balls in it. And I'm going to ignore the labeling for now. We will pick a labeling, but we're not going to care that it looks random yet. And so the two useful facts that we use in the paper about multinomials, one is that the number of balls in each half of a multinomial is a binomial, right? If I throw a ball into 8 random bins, the probability it lands in the first half is 1/2. You do this n times, it's just like a binomial. And then conditioned on the number of balls, the distribution among the half, right? If I tell you 20 balls land in the first half, those 20 balls are still distributed uniformly within that half. So this is, again, just a different multinomial distribution. And so our natural question and the central algorithm that we use is a recursive multinomial algorithm that looks like this. So I'll just run through an example where I'm throwing 30 balls into 8 bins. So I imagine it like a tree, and at the top I sample a binomial, and let's say I sample 18, I send 18 balls to the left, 12 to the right, and then I just recurse, and I do this at every level. And also I can very easily keep track of a start index, just so we have A labeling. So if I send 18 balls to the left, let's just say that I send balls 0 through 17 to the left, and so I just keep track of a start index and the number of balls, and that's enough information to know all of the labels of the balls that went that direction. And I can do this at every level and keep track of how I've sampled this multinomial. And now we'll walk through why this is efficient in both directions. So to figure out, given a specific ball, I want to figure out ball 15, which bin did it land in? So I sampled this top binomial, then I say, okay, ball 15, that's less than 18, so it went to the left. So I sampled that binomial, it's more than 7, it's more than 13. And so I know ball 15 landed in bin 3. Very similarly, if I want to know which balls are in bin 5, I just walk to bin 5, sampling along the way. So I sample my binomial, then I walk to the right, sample left, sample, and right again. And now I know that bin 5 has 3 balls, and the first ball is 21. So I just output 21, 22, and 23. And those are exactly the balls that landed in bin 5. And so this is great. We have an efficient multinomial sampling algorithm, and we can actually, so each path only requires log m samples, and each binomial can be sampled with only log n bits of randomness. This is a fun fact I learned on this project, actually. And so this runs in polylog nm time, kind of ignoring this enumerating pre-images when you have a very big domain and a small range. We can talk about that more at the end. And so overall, if you instantiate this with a PRF or a PRG, you end up getting something called a pseudorandom multinomial sampler that can do this process, which is kind of like an IPRF, except again, we don't care about the random labeling of the balls. But this actually is pretty much enough for us. So if we want to go from a multinomial distribution to an IPRF, we can look at these ball labels. So these are clearly not uniformly or pseudo-randomly distributed, right? Every time any neighboring balls, oh, it looks like I mislabeled something here. Yeah. The consecutive balls are going to land in the same bin or in consecutive bins. So this is definitely does not look like an IPRF. But if we just use a PRP, actually, we can apply an invertible random labeling to the balls after we've done the multinomial sampling. And so what we prove in this paper is that if we sample this multinomial and then we permute all the ball indices, all the ball labels, this distribution matches exactly an IPRF. Okay, and so and luckily a PRP kind of has an efficient evaluation in both directions, like I mentioned before, and so this will work for the IPRF construction. And so kind of in summary, Plinko improves the update efficiency over prior work, like I illustrated. And we are actually the first that achieved this optimal trade-off up to polylog factors between the storage and the query time that was also matched by some later work by Ling Ren and his co-author, that matched this previous lower bound, which was only matched for half of the range before. And we introduced this definition and construction of the invertible PRF, and I'm kind of interested in kind of future applications of how an IPRF can be used, like maybe it can be used in more efficient hashing or data structures, because I think that this like inversion has not been exploited enough. Okay, thanks. I'll take any questions.
Okay, so we do have actually plenty of time for questions if anyone wants to come up. I had a couple of questions actually. So it wasn't immediately clear to me, maybe I missed it. What was the relationship between the domain and the range for your application?
Yeah, so if I'm throwing like in balls into M bins, and in is way, way bigger than M, then there are going to be a lot of balls in any particular.
Is that what it is for your application? And as much?
No. So in our application, we're going to be we throw security parameter times W into W. So there are only on average security parameter many balls in any particular bin.
And then just one other quick question, and then I'll let this eminent gentleman give a talk. I think you mentioned on the last slide, right, there was a work in the prior session shaving off the lambda factor. Can that be
Yes.
combined with your work?
No, so I think, I mean, at least not directly. So the IPRF is really useful for what I think Ling called like the CK20 type of hint structure, which both Piano and RMS are using. But for his work, they use a different hint structure that's based on like some work by Arthur Lazzaretti and Babis Papamanto, which has, it seems very different and it's permutation based. And I think what they do is a very interesting data structures problem, very similar to ours, that solves this problem in a different way.
Okay.
Actually, I had basically the same question, but given it's a permutation, why doesn't update work? Like your thing with updates, because I can immediately find the unique index where the location is. Can't I just add and subtract and be done in time one?
So you're saying instead of using an IPRF, use a PRP?
Well, it's just take the previous paper. Basically, the question is the paper in the previous section updatable in time one without any machinery? Is it
Yes,
like
yes,
oh,
yes.
so they solve your problem more efficiently, basically.
Y-
Is there any advantage of this over that, or that thing is like follow up and?
So I think if there was an advantage, the advantage would probably come in the server download. So I don't think this is something, you should also ask Ling, I guess, to double check this. But I think in the RMS scheme, the server download per query is 2. You download 2 elements. If you have a bounded number of queries, it's a little bit weird. But in the newer scheme, they have to download square root n queries. But the upload is always square root in all of these schemes. And so asymptotically, they're better.
But both schemes are updatable, you're saying, in time one, in constant time, right?
Their scheme is updatable in constant time, yeah.
All right, well, let's thank the speaker again. To start, because we have time.
Sure. You want to sing and dance?
If you like. Yeah, we have about 3 minutes, so we'll just hold off, and you can all relax or run to the next session or whatever you want to do.
Can do an AMA.
Yeah, okay, we're willing. He's offering an AMA for 3 minutes that somebody can record and.
You can ask questions about the talk before it starts. The first question is, why is it in the PIR section?
So can I? By the way, is the next speaker here? I didn't find him in the audience. Oh, hi. Okay.
I was going to go for 40 minutes.
With these parallel tracks, you know, you got to.
Yeah. There you go. He needs to go and wire up.
Academic conference. That's pretty easy. Same excitement. Same excitement.
SBC, yeah, I'm not sure I agree with you. I didn't drink the Kool-Aid as much as you. My perspective is, I'm not sure about this whole field, but I'm protecting people's money from being stolen, so that's a good thing to do no matter what. So this is the thing, people, the talks are short, people very often speak English.
It's hard to fit, you know, yeah.
They think that what happens is they get nervous about the amount of time, so they,
All right, we can go ahead and start. I've never met this guy until today. So, anyway, the next speaker is Yehuda Lindell, and please take it away.
So thank you very much. Firstly, this talk has nothing to do with PIR. That's not the program chair's fault. That's my fault because I had a scheduling problem. So one of the PIR talks graciously was moved to tomorrow. So that's just to So you won't wonder the whole time, what's the connection, what's the connection? Okay, so I'm going to talk about exponent VRFs or EVRFs and their applications. And this is joint work with Dan Bonnet, Iftach Heitner, and Gil Segev. So what's a verifiable random function? It's very simple. You have a pseudo-random function, but now you can add a zero-knowledge proof that you've actually computed that function correctly. So there's some public key or some public verification key that essentially commits you to the pseudo-random function key k, and you can later prove that this value y that you provided previously is correctly computed based on that k. And VRFs have many applications and have proven to be very, very useful. So what's an exponent VRF? Well, it's exactly the same idea, except that instead of me providing the output of the PRF directly, the little y, I'm actually going to provide that y times g, or g to the y. That's why it's exponent, because in multiplicative notation, it's g to the y. So that's all I'm providing, together with a proof in exactly the same way. Okay, so it's a VRF, but instead of giving you the output directly, I'm giving to you in the exponent. So in elliptic notation, I'll give you capital Y, which is y times g, and I still want to be able to prove to you efficiently that this value is correctly computed. And we also require that there's a simulator that can extract the private key k from some key generation phase, and that enables you to simulate because you know what the private key is already, so I can know into the future what this party, if they're corrupted, what values they're actually going to provide. So that's an exponent VRF. And what's the rationale? Why are we interested in this primitive? So there are many cases in threshold signing where a party has to generate some scalar Ri and provide big Ri, which is little Ri times g. And with an EVRF, you can provably generate this via a pseudo-random function. Okay, so rather than just me choosing the Ri by myself, I'm now forced to choose a very specific value that I've already committed to, but is still pseudo-random. Okay, that's nice, but so what? Why is this useful? And the answer is actually that we have many, many applications for this single, very simple primitive. Firstly, we can do two-round, fully simulatable multi-party Schnorr signing. And all previous constructions of this were either game-based definitions only, required a setup, or use non-standard assumptions. Likewise, we can do two-round, fully simulatable two-party ECDSA signing. I think that we can do also multi-party, but that's an open question. We haven't done that. We can do both of the above with deterministic signing. And deterministic signatures is something that many people are interested in or want, and it's actually very challenging to do because if the honest parties use the same randomness because they're deriving their randomness from the message with the PRF, but the corrupted parties don't, then everything completely breaks and you can extract the secret key. So doing this deterministically in an efficient manner is actually very, very challenging. We can do one round fully simulatable distributed key generation. You need a nonce or timestamp or something. But otherwise, anyway, even if you don't, you'll just generate the exact same key. It's not sure that's such a problem. And we can also do MPC-friendly HD derivation, which is essentially deriving keys. You generate one key, and I can derive many keys for, like in BIP32, what's done in the blockchain world very often. But I can do this MPC-friendly, where I'm actually enforcing correct behavior. And all the protocols that we have for this are UC secure. They're fully simulatable. Secure for any number of corruptions, and are under standard assumptions. They do use a random oracle because our constructions for EVRF also use a random oracle. So hopefully I've convinced you that there are many applications. It's a very simple primitive, but it's very, very useful for in many, many places. And the question is why? Why is it so useful? What's common between all of these things? And why does the fact that I have this EVRF primitive actually help me get full simulatability versus some sort of game-based definition? And also, what's an interesting question is, why do I care about full simulatability? So that's what I'll try to answer all of those questions for the rest of the talk. So, as I said, previous results, previous constructions of two-round protocols, why they're not simulatable, not efficient, rely on non-standard assumptions, or have some sort of setup that you need to do, pre-processing that you need to do on an ongoing basis. Okay, let's start with why do we care about simulatability? Because that's really what we're getting in all of these things. You can do all of these things in different ways without the same level of security, so why is this important? And there are actually a few answers, but the one answer I want to focus on is that of composition. So when I have UC security or simulatability with universal composability, then I have a guarantee that my protocol is going to remain secure no matter what else is running concurrently with that protocol. And with game-based definitions, it's not necessarily the case, or in general, composition with completely different protocols is just not covered. Now, very often you can say, but if I'm using fully independent random keys, then I should be fine because nothing else is going to be related. You can sort of argue that, but if the keys that you're using are not uniformly distributed or are not completely independent of everything else, then you actually can't argue that with standard-based game-based definitions. I'm not saying you can't build a game-based definition that will sort of work this in, but it's certainly not covered in game-based definitions. And then the question is, we can ask is, in practice, are signing keys fully independent and uniformly distributed? You would hope yes, because you're cryptographers, but the answer is absolutely not. And especially in the blockchain space, keys are not independent. There are these HD wallets, hierarchical deterministic wallets where you derive keys. And the way they are derived is just, they're not independent. So there's this thing called BIP32, and there are hardened derivations and normal derivations. And depending on what type of derivation you're doing, there's certainly not independence between keys. For normal derivations, certainly not. Even for hardened derivations from parents to siblings, the connection is known. And so you cannot actually argue that if I have a game-based definition that's assuming random keys, and they all do, that it's actually secure in this model. Another thing that can happen is that people generate keys however they want to. They may get mnemonics, but they may also have, okay, I have a mnemonic, I'm going to have a partially overlapping mnemonic, so I'm using randomness which is related. Or maybe I'm going to generate my ECDSA key using my name and my age. Yes, I'm old. Or maybe my age and my year of birth. And as cryptographers, you say, this is a terrible idea, you should not do that. And you're absolutely correct, I should not do that. But yet people do that. And then the question is, what do I want to do when I'm building an MPC protocol? So one thing I can say is, I'm responsible only if you're responsible. If you're not responsible, it's your problem. That's certainly a valid approach, not necessarily a great one, but a valid one. Another approach is to say that people sign using local signing schemes. So I can just generate my signature locally. And I want my MPC protocol to be at least as secure as that. So on my MPC protocol to give you this separation and no single point of attack, and you need to attack many entities. But I really want to make sure that if you, that I'm no worse than a local signing. And if I have composition, then that's what I'm going to get. My protocol is going to be as secure as it is using Yehuda 54 exclamation mark, and no worse. But if I use a game-based definition, I can't argue any security about that. Okay, so how do EVRFs actually help you get simulatability? And the answer is that in all of these situations, the HD derivation is a little bit different, but I'll focus on key generation and signing for ECDSA and Schnorr. There's something that we always need to do, which is to generate some big R, which is little r times G, where little r is shared amongst the parties participating. And this is the same thing that we need to do over and over again in every single scenario. And the naive solution for this is very simple. Each party randomly chooses little ri, computes big Ri by multiplying it by G and sends it to everyone, and then we sum them all together. And that's the result, and that's what we can use. And this is a terrible idea, because a corrupted party can see everybody else's big Ri's first and then choose their value to be based on the others. And if you do this really naively, then you can actually completely break the protocols. And therefore, protocols getting too round do something where they multiply it by some sort of coefficients, and these coefficients depend on everything, and this somehow limits the bias that you can get. It limits it in some sense, but it's still, you can certainly still bias, because I can see everybody else's result, and I can just try different values. So if it's really important for me that the third byte of R, big R, is going to be all zeros, I can easily do that. Okay, so you can certainly bias, and once you can bias, you cannot achieve full simulatability, because full simulatability basically means I'm getting this standalone generated signature that was generated by a trusted party, and I need to somehow make the execution equal that. So all of these approaches completely fail when you want composition. So how do we prevent it usually? Very simple. I commit to the RI instead of giving it to you in the clear. And after everybody gets it, then everybody opens. Very, very simple solution. Now, if the commitments are binding and non-malleable, I can't make my commitment depend on your commitment, and therefore we have complete independence, and this is great and completely solves the problem. And in the usual case, this is absolutely fine, but if you really want 2 rounds, and in some cases you want 2 rounds, then in order to generate, I'm already spending 2 rounds to do that, so I need a 3rd round at least to finish the signing process, and my protocol is no longer 2 rounds. So this way of working just doesn't let me achieve what I want to achieve. So how can I do this in 1 round? It's essentially, it's not just key generation, right? The same primitive we're using for signing as well. And it seems inherent because if I'm revealing in the first round my output or my big RI, then it seems impossible to prevent an adversary from biasing because the adversary is rushing and can always see that first. And the answer is, if the corrupted party or the parties are not able to choose any RI, in fact, they're committed to their RI ahead of time, then they can't bias. Because even if they see everybody else's RI, they have no choice. This is the only value that they can provide. And in fact, formally, since the simulator can know ahead of time what you're going to provide, then you can set things up and the simulation goes through. So how can we do that? And the answer should be obvious by this stage. It's to use an exponent VRF. So how does it work? Each party computes their RI by computing an RF or an EVRF on, if it's key generation, then on a nonce or timestamp. If it's signing, for example, to compute it on the message as the input. That also makes it deterministic, and provide a proof that this is correct. Now, everybody's committed ahead of time. They will provide these values. We check the proofs, we sum it up, and now we have the value. And because I have no freedom in choosing my value, I cannot bias the output. And it also gives me deterministic signing for free, so to speak, because I can't change anything. If I want specifically not to have deterministic signing, then I can add some sort of nonce or timestamp or something inside as well. Okay, so I hope that makes sense as to why this EVRF helps us achieve simulatability and prevent bias, even if I'm just doing this in a single round. So we can, unlike beforehand where I had to commit and then open, now I can just send the value straight off and we're done. Okay, so how do we construct these EVRFs? Okay, so that's the next challenge, and how efficient is it? So we have 2 constructions in the paper. The first is based on DDH, and I thought I had an animation here, but I don't. So the construction works by using a well-known pseudorandom function, which is simply mapping via random oracle the input to an elliptic curve point, that's h of x, and then multiplying it by k. By DDH assumption, this is a pseudorandom function. And the problem is, if you think about this construction, that I end up getting an elliptic curve point or a group element as the result, but I need a scalar. So, because I need to multiply that now by a g. So I have 2 groups, a source group and a target group, and I'm going to compute the PRF in the source group and use the scalar coming out of that, the x part of the point coming out, as the scalar in the target group. Okay, so if the order of the target group is the same field size as the group size of the source group, then everything matches up and I can feed it in and then actually use the output of the first part, the x element, as the scalar in the second part, and then get my EVRF. So how do we do it? You compute P, which is k times h of x. You take the x coordinate of the result. You then multiply that by times g in the target group. So I'm now in a different group. And now I just need to prove in zero knowledge that everything is correct. Okay, that's the big question. How do I prove in zero knowledge that this is correct? So it turns out that using the chord method for elliptic curve operations, this is just, we have a series of equations. And that series of equations I can write in R1CS. And if I can write in R1CS, I can then use bullet proofs to prove that statement to be correct, or any other ZK system that you may happen to prefer or love or not love. We did this, and despite our very optimistic estimates written in the paper of some tens of milliseconds, maybe 70 milliseconds, 60, 70 milliseconds, I'm not sure what's written in the paper, we were off only by an order of magnitude. It actually turned out to be much more expensive than we thought. So we have 800 milliseconds prover time, 200 milliseconds verifier time. We actually are pretty sure we can reduce that to 300 and 150. We didn't bother doing it because in the next slide I'll show you another construction that we thought would be much less efficient, which turned out to be much more efficient. So this EVRF, by the way, is actually implicit already in MuSigDN. Our construction is a little bit more efficient, but much more importantly, at least in my mind, the contribution of this paper is not so much in having a certain construction, but in the conceptual contribution of having actually this primitive, and noting that this primitive can be used in many, many different places, and it's interesting within its own right. Who knows, maybe it's even useful in PIR, just to connect to the session, and also being able to come up with different constructions, because I now have isolated this as an interesting thing with its own right. So the second construction uses PIR, and usually we think of this to be much less efficient, but it turns out not to be. So the way this works is we map the ciphertext, we map the message to a ciphertext using a random oracle. I said my constructions are based on random oracle, unfortunately. So we just hash the input to a random value in Zn squared for PIR, and the EVRF secret key is the PIR secret key, so we just invert, or we decrypt, actually. We decrypt the ciphertext, take mod Q, and this is going to be the pseudorandom value. It's very easy to see this is going to be pseudorandom value, because if you start off with a random oracle mapping the ciphertext, you're going to be encrypting a random value, and now we have the output to be little y. And now we compute big Y is Y times G, and we just prove that the PIR ciphertext encrypts the discrete log of big Y. This is actually what we called PDL in the 2017 paper on two-party ECDSA signing. And if you look at the running times in that paper, it's quite an expensive proof because it requires a range proof. Because the problem is you're in different orders and you have to make sure that you're not going to go wrong. And it turns out that you can use bullet proofs for this as well. And we actually have a new PDL proof, which is really, really efficient. And just to give you an idea of how we did it, usually to do a range proof for PIR, you Pedersen commit to something in the finite field because it needs to also be big, and then you prove equivalence, and then you prove a range proof on this Pedersen commitment. But in finite field, and those operations are also very expensive. But what we actually could do is we used bullet proofs, and we committed to two 128-bit values in an elliptic curve group. So we used Pedersen commitments on an elliptic curve group, and then the bullet proofs are much, much, much more efficient. And then you just show that the first ciphertext plus 2 to the 128 times the second ciphertext is the original value. So this actually turns out to be very, very efficient, and we end up getting 80 milliseconds prover time and 80 milliseconds verifier time, which is very, very efficient. Again, is it as efficient as doing Schnorr signing without an EVRF and using an extra round? Absolutely not. But if you want 2 rounds and it's important to you, then this is very, very reasonable, at least in a blockchain space, but in other spaces as well, depending what you're using signing for. So in summary, we present a new conceptually simple primitive. The constructions are not that simple, but they're not that difficult either. And we show that it has a very, very large number of applications: 2-round threshold signing, deterministic signing, 1-round distributed key generation, and MPC-friendly HD derivation. If I have time, I'll explain why 2 rounds can be interesting. Do I have another minute? So 10 seconds, I would say, the reason that I think 2-round can be interesting is if I have one party who I want to be an offline party, then all the other parties can compute the first round. We can give that to the offline party. The offline party then computes their first round and second round and gives it back, and I only have one interaction with that. That's the only use case that I think is really interesting. But I do think it's interesting from a theoretical perspective to ask, can you get 2-round fully simulatable in a concretely efficient solution? And the answer from this paper is yes. Thank you very much.
Looks like we have a question. Yeah.
For the talk, it's a really, really cool primitive. You said you use PIR encryption in the second scheme. Is there a particular reason why not use something else like Okamoto Uchiyama or some other, I don't know, RSA-based?
It will work with anything which is additively homomorphic.
But presumably not El Gamal because you need to decrypt.
El Gamal, I can't. El Gamal in the exponent is going to be additively homomorphic, but I can't decrypt. So I can't. I won't be able to get the little y.
So would you expect to get more efficiency if you use CL15 over class groups?
So the class groups, from my understanding, give you the advantage of you're in the same order, so you maybe won't need the range proof. But the construction itself is more expensive. It could be more efficient, but I'm very, very conservative in assumptions. For me, PIR is semi-standard assumptions. So in my PhD thesis was one paper I wrote in my introduction that we use DDH, and I wrote in the abstract I use standard assumptions, and the assumption was DDH, and Oded Goldreich crossed it out and said, DDH is not a standard assumption.
All right, cool. Thank you.
Let's thank the speaker again. All right, the final speaker of the session. Do we have the slides? It's Aditya Hegde, and go ahead, take it away.
Thanks for the introduction. Hello, everyone. I'll be presenting enhanced trapdoor hashing from DDH and DCR. This is joint work with Geoffroy and Sehan. So in this work, we focus on the following setting. We have a sender, Alice, with an input X, and we have a receiver, Bob, with an input Y. And we want to compute a function on their joint inputs using only two messages. So in the first message, Bob sends an message based on his input, and Alice responds with her message, which allows Bob to compute the output. What we want is that these messages should preserve the privacy of the inputs. And the main question that we're interested in is, can we construct secure protocols that are very efficient with respect to their communication costs? In particular, we'll focus on the setting where Alice has a long input and Bob has a short input. In the ideal world, where parties trust each other and we don't care about privacy, Bob can simply send the short input to Alice. Alice can compute the output and send it back to Bob. And the total communication is proportional to the length of the short input plus the function output. And really what we want is to build secure protocols that are as efficient as the insecure or the ideal world. And doing this also helps us understand what is the overhead of achieving privacy. Trapdoor hash functions are a primitive that were introduced by Dotling, Garg, Eshai, Malvolta, Moore, and Ostrovsky that are very useful for building primitives in this setting. So what is a trapdoor hash function? Using a trapdoor hash function, Bob can encode his input and compute an encoding key and a trapdoor, and he sends the encoding key to Alice. Alice can hash her input, and then using the encoding key sent by Bob, she can compute a hint, E. Then using the hash and the hint, Bob can and the trapdoor, Bob can compute the function output. As before, privacy requires that the messages exchanged between the parties preserves the privacy of the input. But what makes trapdoor hash functions interesting is their efficiency property. So what we want is that the hash digest can be polynomial in the security parameter, but it must be sublinear in the size of Alice's input. Moreover, the hint E must have high weight, which means that asymptotically it should be as large as the function output. For example, we don't even want a multiplicative overhead in terms of the security parameter. In their work, Dotling and friends introduced a trapdoor hash function, which supports evaluating the inner product function over inputs. The encoding key is lambda times Bob's input. The hash digest is independent of Alice's input. And the hint is exactly, it's rate 1. It has exactly the size of the function output. And they get it from a variety of assumptions, including DDH and DCR. And in this work, what we ask is if we can improve the functionality of trapdoor hash functions based on group-based assumptions. And we show that indeed we can do this. And we construct trapdoor hash functions that have three enhanced properties. First, they allow computing a larger class of functions, which we call bilinear NC1 programs. where parties' inputs are first expanded by an NC1 function before computing an inner product. Next, our encoding keys have high rate. It's, the encoding key is linear, almost linear in the size of Bob's input with an additive factor, a small additive factor. And finally, the construction enjoys a property which I'm calling for this talk as reusability, where once Bob sends an encoding key, which encodes some input y, and then later when they decide on functions f1, f2, f3, Alice can use the same encoding key to compute hints for all these functions. And once she sends the hash and the hints to Bob, he can compute the output for all the functions. Finally, I'd like to note that our DDH-based construction gives hints that are slightly larger, while our DCR-based construction gives rate 1 hints. And with these three properties, we get a lot of improvements to existing applications to trapdoor hash functions, which I'll go over next. So because our encoding keys are rate 1, we get batch OT with optimal rate from DDH. So what is OT? In oblivious transfer, Alice has 2 inputs, each of them a single bit, and Bob has Bob gets one of the messages based on his input. Batch OT is running n independent instances of OT simultaneously. In the ideal world, batch OT would require 2n bits of communication, as we just saw. And now let's try and instantiate batch OT with our trapdoor hash function. So when we try and instantiate it with trapdoor hash function, the message sent by Alice to Bob, the hash digest is already sublinear in Alice's input, and the encoding is high rate. This is just by definition of the trapdoor hash function. But now, because of the compactness property, even the first message sent by Bob to Alice has high rate, which means that we require around 2n bits for communication. And this gives us rate 1 batch OT from DDH. And our construction also has semi-honest statistical sender privacy, which means that Alice's input is information theoretically private. Compared to prior work, the batch OT with optimal rate from minimal assumptions required LPN in addition to DDH, so we remove the LPN assumption. And previous constructions from DDH either had lower rate, half the rate, and also required a PKI setup. The application, the construction of batch OT then implies a number of improvements to related primitives, and which were previously not known from DDH. Very briefly, we get string OT where the sender to receiver communication is sublinear in the string length. We get rate 1 lossy trapdoor functions with rate 1 public keys, and if we allow for a reusable CRS, we get public keys which are sublinear in the size of the input. And we get PIR where the client to server communication has high rate. Again, all of this are from DDH. We also have other applications to evaluating and branching programs over encrypted input and correlated symmetric PIR. The next application I want to talk about is the compactness, is what we get from our expressivity, which is we evaluate a larger class of functions. And because of this, we get sublinear two-party computation from DCR, where one of the parties' inputs is information theoretically private. And and this supports evaluating layered circuits. And this follows from the fact that bilinear NC1 programs help evaluate log-log depth circuits, which in turn shaves the log-log factor from the communication of the 2PC protocol. So, this is the communication cost of our protocol. We get linear overhead in the computationally private input. We get sublinear communication in the information theoretically secure input. And we get a log-log factor saving in the circuit size. So in the interest of time, let me be brief here. Yeah, so previous results, similar results were only known from FHE. And prior group-based constructions either had a slightly larger, they had a linear overhead in both inputs and had stronger assumptions. Finally, our reusability property gives us optimal communication in an amortized setting, where Bob uses different inputs to evaluate with Alice's input. So in this setting, we consider protocols where Alice and Bob send a pre-processing message. And later, when Alice, and this message is simultaneous. And later, when when Bob gets an input y1, he sends a message to Alice, receives a response, and then learns the output. And he can do this arbitrarily many times. So how do we construct this from trapdoor hash functions? In the pre-processing step, Alice sends a hash of her input, and Bob samples a PRF key and sends an encoding of the PRF key. Later, when Bob gets his input y, he uses the PRF key to encrypt his input, and he sends the ciphertext. Now, the ciphertext ensures the privacy of the input because the encoding key preserves the privacy of the PRF key. Later, Alice computes a function where you first decrypt the ciphertext and then evaluate the public function. She computes the hint and sends it back to Bob, and then Bob gets the output. And this again by encrypting the PRF at different points, we can do this arbitrarily many times. And what I would like to note here is that the function that Alice evaluates using trapdoor hash takes in Alice's input x and the PRF key as input, but has the ciphertext hard-coded in it. So this function is determined only after Bob sends the ciphertext. But Alice is still able to use the encoding key that was sent in the pre-processing phase because of the reusability property of the trapdoor hash function. Finally, the message sent by Bob to Alice is rate 1 because of the hybrid encryption. And the message sent by Alice to Bob is rate 1 with DCR because it has rate 1 hints. So we get optimal communication per query from DCR. So using this template, we get optimal pre-processing symmetric PIR from DCR, where the pre-processing messages are sublinear in the size of the database. And we get rate half private set intersection and fuzzy private set intersection from DCR, where again, the pre-processing messages are sublinear in the size of Alice's input set. So in the time that I have left, let me go over how we construct our enhanced trapdoor hashing functions. So at a very high level, what we do is we combine two primitives from existing work, something known as staged homomorphic secret sharing and trapdoor hash functions. An alternative view of our construction is that we're extending previous work by Abraham, Roy, and Scholl on succinct HSS to support bilinear NC1 programs. So our starting point is the staged homomorphic secret sharing scheme. So what does this allow? So here, Bob samples a key pair. And using this key pair, he can encrypt his input and compute shares of Alice's input. And now if parties have the ciphertext and their shares, they can non-interactively compute shares of the output for any bilinear NC1 program. Our key contribution, our technical contribution, is building a protocol for succinctly distributing the shares of Alice's input. So the way it works is Bob sends a message. Alice can use this message to compute her share. And then Alice sends a response, which allows Bob to compute his share. And turns out this suffices to build trapdoor hash functions. And the reason is because, yes, and the messages are succinct. They're sublinear in the size of Alice's input. And turns out this is enough to build trapdoor hash functions. How does it work? So again, Bob samples the key pair for staged HSS. He then samples a PRG seed K and encrypts his input under the PRG seed and encrypts the seed itself using staged SSS. This is just hybrid encryption. He sends the ciphertext along with his share distribution message. Alice computes her share and then runs staged SSS to get the circuit output, the function output. She then sends her output share along with the share distribution message, using which Bob can, again, compute his share of Alice's input, run staged HSS, and compute the output share and reconstruct the output. And just to go with the communication efficiency, because of hybrid encryption and the succinctness of our share distribution protocol, the Bob's message has rate 1 in his input. And because, again, the share distribution is messages are succinct, the message corresponds to the hash of the input, which is succinct. And the output share is an additive share, and so it's rate 1. So now let's discuss how to build the share distribution protocol. Here, let's start by understanding the structure of staged homomorphic input shares. So Bob essentially samples an Elgamal key pair, and Alice's share of her input are actually Elgamal encryptions of every bit of Bob's secret key multiplied with her input. And here, x1 to xn is just the long input that Alice has. And here, for the rest of this talk, let's just focus on one particular bit of the secret key. And that's we've just expanded. The same randomness will not be used for all ciphertexts, but this is enough to understand the key techniques. And Bob's share of Alice's input is just the randomness component of the ciphertext. It's just the commitment to randomness. And what we want is now to build a succinct protocol for distributing these shares. Well, since Bob's share just consists of random values, a naive attempt is Bob samples a PRG seed, uses it to compute R1 to Rn, sends the seed to Alice, using which Alice can compute the randomness component. She can then use Bob's public key to also compute G to the Sk times Ri. But she still does not have G to the B times Xi. And it seems like to compute this, we really need Bob to send G to the B, which would be insecure, because B is a single bit, and that would leak a bit of the secret key. So our key observation is that we can actually compute this function using techniques from trapdoor hashing. And so let me show you how. So the goal is, as we just saw, is for Alice to get Elgamal encryptions of a secret key that Bob has, a bit of the secret key that Bob has, times her input. And Bob wants the randomness components of these ciphertexts. So to do this, Bob samples n group elements uniformly at random and a random value R1. He then sends the group element as well as the second vector, which is each group element to the Sk times R1. And the first element is additionally shifted by G to the B, right? So now Alice uses the first vector to compute a hash of her inputs. And let's call this hash digest H. Now when she uses the second vector to compute a hash of her inputs, some simple calculation shows that she actually ends up with H times Sk times Ri times G to the B times Xi. So if we compare what we wanted and what we have, it's very similar, except that we have H as the base instead of G. But turns out this is fine for staged HSS evaluation, as long as we also transform the first component to be H to the Ri. We really want it to be Elgamal ciphertext, essentially. OK? So now we have a way to get the second component for the first ciphertext. Now, if Bob samples another value R2 and sends another vector with the shift applied in the second position instead of the first, a sort of symmetric argument shows that Alice will end up with Sk times R2 times G to the B times X2, where you get you get B times X2 because the shift is applied to the second component. And similarly, if Bob sends n such vectors, Alice can compute the second components of all the ciphertexts. And we can use the first component of all the ciphertexts can be computed in a similar manner. Finally, if Alice sends the hash H to Bob, then Bob knows each of the RIs because he sampled it before, and he can just compute H to the RIs. So we've really gotten what we wanted. But I promise, so this hash needs to be randomized, and here I've not included the randomness. If we don't randomize it, it's no longer secure. It no longer hides Alice's input. But it turns out this can be, you can randomize the hash and still preserve correctness, and it doesn't require much work. So I promised a protocol with succinct communication. But here, Bob is sending n square elements, and Alice is sending just a single group element. So it turns out to get succinct communication, we can use a rebalancing trick, because Bob's message is reusable with different hashes. And with rebalancing, we get succinct communication. Some concluding remarks. So the approach we just went over assumes or requires circular security of El-Gamal, and the same approach can be used with DCR. To get it from just plain DDH and DCR, we need to extend these techniques to circular secure encryptions under these assumptions. Also, the DDH-based staged HSS algorithm has inverse polynomial error. It has noticeable error. And ensuring we get a trapdoor hash function with negligible correctness error requires some building some new techniques, because it also affects privacy. And that's all. Thank you.
Okay, we have time for a question, if there's a quick question. No? All right, so why don't we thank the speaker and all the speakers in the session again. And now we have, I think, a 15-minute break, and then another